Today we want to continue solving oblique triangles and want to look at some different situations. So far, we've done one problem where we had two sides in the included angle, so we use the law of cosines. The second example that we had, we were given three sides, so we use the law of cosines to find an angle. We also had an example using the law of cosines where we're given three sides that wouldn't make a triangle because one of the sides was bigger than the sum of the other two sides, thus failing to make a triangle. So now let's look at a different situation. Here I have two angles and a side. So if angle alpha is 72 and angle gamma is 54 and side B is 27.9, we'll notice that we don't have the set of opposite parts. But the important thing that we have is two angles. As soon as you have two angles, you need to subtract to find the third angle. We have two angles. We're going to subtract to find the third angle. That should be our first thing. So 72 plus beta plus 54 is 180 degrees. As soon as we know two angles, we should subtract to find the third angle. So 180 minus 72 minus 54. 54 is 54. If you have two angles, you subtract to find the third angle. Now we definitely have a set of opposite parts. We notice something else about this particular triangle. What do we notice about this triangle? This is an isosceles triangle. We have two equal angles. Therefore, we have two equal sides. Equal angles will be opposite equal sides. If two angles are equal, the two sides opposite those angles must also be equal. Since angle beta is equal to angle gamma, side C is equal to side B. So beta equals gamma means that side C is equal to side B. So that was convenient. Sometimes we're solving triangles and we get lucky about things. And we want to make sure that we identify when we get lucky about things. Now I've got we're 2/3 of the way done. We have a set of opposite parts. Once we found angle beta, we have a set of opposite parts with B and beta. We got kind of this second side for free. We need to find side A. And for that, we will use the law of sines because we have a set of opposite parts. So I'm going to say sine of alpha over A is equal to the sine of beta over B. So sine of 72 over A that we're looking for is equal to the sine of 54 over 27.9. So that means that A is 27.9 times the sine of 72 divided by the sine of 54. So it looks like side A is 32 point, we'll round it 32.8 since we're done. Round. If we didn't happen to notice that the that beta and gamma were equal to each other, and we tried to use those parts in the law of sines, they would just cancel out. So I'd have sine gamma over C is equal to sine beta over B. So C would be 27.9 times the sine of 54 divided by the sine of 54, which gives us 27.9. So it would still work out if we didn't happen to notice that this was an isosceles triangle. Any questions? Observe, okay? Situational awareness is key. All right. So let's adjust things a little bit. Let's say that alpha is 72 degrees, and let's change up gamma. So instead of 54, that gave us an isosceles triangle. Let's go with 64. And side B can still be 27.9. Our reaction should be the same. We see that we have two angles. We immediately want to subtract to find the third angle. So alpha, gamma, so beta is 180 minus 72 minus 64 this time. So that's going to be 44. Now we have all the angles, and most importantly, we have a set of opposite parts. I've got angle beta and side B. That means we should use the law of sines. It's not the first thing that we're doing, so we don't have to worry about the ambiguous case. We're also using the law of sines to find a side, so we don't have to worry about the ambiguous case. Those are two reasons we don't need to worry about the ambiguous case. So I'm going to take the sine of alpha over A is equal to the sine of beta over B. So sine of 72 over A is the sine of 44 divided by B. Oh, B is 27.5. The nice thing about this calculation is that the 44 has not been rounded off, so I don't have to worry about rounding error in this case. Just punch it in the same way I would write it. And side A is 38.2. Now this has been rounded off. So if I start using this in calculations, I'm going to want to use all those decimal places. I'm not going to clear this off my calculator in case I need it in the next step. I would like to avoid using 38.2 because it's been rounded off. Hasn't been rounded off all that much, but it has been rounded off. It's a little bit. In this case, since I don't want to use rounded off information, I'll just use beta and B to find side C. So for side C, I'll set up sine of gamma over C is equal to sine beta over B. So all I have to do is edit my previous entry. So if you notice above enter, there's a blue entry. So if you press second and then enter, it'll give you the same thing that you just typed. And then we can just go back and change our 72 from alpha to a 64 for gamma. Now I have all 6 parts. We'll want to do a reality check. Want to make sure that our answers make sense. Is the biggest side opposite the biggest angle? So the biggest angle is 72 and the biggest side is A at 38. So yeah. And the smallest side is opposite the smallest angle. Side B is smallest at 27.9 and angle B is smallest at 44. So at the very least, our solution passes the reality check. So replace largest with middle and smallest. Make sure everything works out. How's everybody okay? Everybody looks very stuck. All right. So if you have 2 angles, you have 3 angles. So when you're reading about this, you're going to find the book breaks down into an angle side and an angle side angle. Those 2 are the same because both of those, the angle side or angle side angle, you have 2 angles. If you have 2 angles, you're subtraction away from having 3 angles. So just lead with subtraction to find the 3rd angle. Even if on this problem, all you had to do was find one of the sides A or C, you're going to have to find the 1st angle anyway. So just open up, if you have 2 angles, open up with finding the 3rd angle. So we got those 2 cases where we have to use the law of cosines. We don't have a set of opposite parts. We have 3 sides or 2 sides and the included angle. If we have 2 angles, then we just subtract to find the 3rd angle. Then it's just the law of sines. We didn't have to use the law of cosines. In fact, we couldn't use the law of cosines because we only had 1 side to start with, and the law of cosines requires 3 sides or 2 sides and the included angle. So that was never an option. Also note that once we had side A and side B, we could have used the law of cosines to find side C. But since using the law of sines is going back and changing 1 number in the calculation that we just did, we should just use the law of sines again. Any questions? I don't think I've ever had a student that would go back and for side C in this situation, use the law of cosines as the last move in a problem. That would be really weird. That would be like someone saying, well, I don't want to use the law of sines again. I've already used the law of sines. I want to do something different. So I'm going to use the law of cosine. It's kind of like in a song. You can't rhyme a word with itself. You know what I mean? Like there's some songs out there where they rhyme a word with itself. And I'm like, well, no, that's a mistake. Like with Madonna was like, well, don't just stand there. Let's get to it. Strike a pose. There's nothing to it. I'm like, well, no. You can't rhyme to it with to it. That was stupid. That's bad writing. There was exactly one instance where this was okay. There's one instance where rhyming the word with the word was okay. And that was War Pigs and that. Because, I mean, Black Sabbath. I don't know why that song gets a pass from me. Because every other time that happens, I get so mad. I'm like listening to the song, I'm like, did they rhyme to it with to it? Son of a. And I want to buy a ticket to that show just so I could boo that. Like I'll wait for Vogue to come on. Let's get to it. Ooh, okay, we can go. Of course, Madonna would be like, well, I already got your money. I don't know what you're complaining about. Damn it, I should have just tweeted it. But then I'd have to get Twitter. That's not it. But then War Pigs comes on and I'm like singing along. I'm like, well, did you just rhyme masses with masses? Well, shut up. It's Black Sabbath. I don't know why Ozzy gets a pass. What are we talking about? Ah, yes. We've got to talk about the ambiguous case. Recently, I got the complete Sherlock Holmes in audiobook form. And so now I cannot read this without hearing the guy that voice that was recorded. And I can't remember his name right now. Kind of bad, but it was really good. But now all I can hear is the ambiguous case of the law of sine. Let's talk about the ambiguous case of the law of sine. The setup here is we're going to have a set of opposite information and another side. So the setup is a set of opposite information plus another side. If we have a set of opposite information plus an angle, that's this up here. No trouble at all. Because if it's a set of opposite information plus an angle, that's two angles, that's three angles. So the ambiguous case of the law of sines means we have a set of opposite information plus a side. Set of opposite parts So what we're going to do is we're going to name the three parts. There's going to be the given angle, the side opposite the given angle, and the other given side. So there are the three parts. There's the given angle, the side opposite the given angle, and the other given side. That's a set of opposite parts, a given angle and the side opposite the given angle, and a side, which we'll call the other given side. The number of triangles will be determined by the side opposite the given angle. That's where we have control. Let's draw a picture of what's going on. Let's start off by drawing the line where the third side goes. Then in this corner, I'm going to write the given angle. So in this corner, we're going to have the given angle. That means over here somewhere is going to be the side opposite the given angle. So up here is where we're going to draw the other given side. The side opposite the given angle has to connect the other given side to the line where the third side goes. The side opposite the given angle must connect the other given side to the line where the third side goes. What this means is that we could end up with different numbers of triangles. It could be that the side opposite the given angle is too short to cover the distance. There is a minimum height requirement to make a triangle. So the side opposite the given angle has to be able to clear this distance. There's a minimum value for the side opposite the given angle. If the side opposite the given angle is equal to that height of this triangle, then we can have one triangle. But if it's less than that height, we will not get any triangles. So we get 0 triangles if the side opposite the given angle is less than the height. If the side opposite the given angle is less than that height, then we have no triangles. We try to install the side opposite the given angle, it just kind of like hangs there from the other given side. It can't reach the line where the third side goes. Can we imagine it? Just want to imagine the little green side opposite the given angle, just kind of like dangling from the other given side. Oh, I can't read. Oh, that's cold. I made the side opposite the given angle green, like the Mora. I'm going to drop it off the other given side. Cold. That was cold. So we get zero triangles if the side opposite the given angle is too short. That is, it's less than the height. We get exactly one right triangle if the side opposite the given angle is equal to the height, like exactly equal to the height. So we get one right triangle if the side opposite the given angle is equal to the height. Perfect fit. So I want to connect the side opposite the given angle from the other given side to the line where the third side goes, and it will fit perfect if the side opposite the given angle is equal to the height, and we'll get one right triangle. So imagine instead of just a too short side opposite the given angle dangling from the other given side, it's exactly tall enough, and it can just barely touch the line where the third side goes. Perfect fit, one right triangle. If the side opposite the given angle is more than the height, then we could end up with two triangles. So this is the case we got to watch out for. Two triangles. If the side opposite the given angle is greater than the height, I'm color coding them all now, so I'm stuck with it. There's going to be an addendum to this. So now I want you to imagine hanging from the other given side, a side opposite the given angle that is a little bit more than the height. Then I can put it in two ways. I can have the side opposite the given angle connect to the other given side here. Or I could swing it over to the other side of that vertical. And make two triangles. So I could have, here's one length for that third side, or I can have another length for that third side. More importantly, I can have two angles. If the side opposite the given angle is greater than the height. But there's a point where I can't swing this to get two triangles. If the side opposite the given angle is greater than the other given side, then if I have a side opposite the given angle, it's greater than the other given side, then I try to swing it, I can swing it over here and make one triangle, but if I try to swing it all the way over here, it just goes all the way around and lands back on that first triangle. It's too long to make a triangle go in the other direction. So it's the two triangles case if the side opposite the given angle is greater than the height but less than the other given side. The two triangles happens because I can take that side opposite the given angle hanging from the other given side and put it in two places. It swings back and forth and hits the line where the third side goes twice. But if the side opposite the given angle is greater than the other given side, I don't have one swinging over this way to the left. It just goes all the way around and lands on the other given on the line where the third side goes. So we're back to one triangle. If the side opposite the given angle is greater than the other given side. There are the four possibilities in the ambiguous case for the law of sine. The setup is to imagine the floor being the line where the third side goes, put an angle on the floor, and have the other given side making that angle, and then trying to fit that side opposite the given angle, connect the other given side to the line where the third side goes. It could be too short. It could be exactly the right length. It could be a little bit too long where we can make two. Or if it's longer than the other given side, which is not going to be the case because my hand is not as long as my forearm, it just swings all the way around and we can only make one triangle. Here's the good news. We don't have to know how many triangles there are going to be going in. If we just assume there are going to be two triangles, the numbers will tell us how many there are. Let's take a quick break, come back and do an example with this ambiguous case of the law of sine.